All right, welcome to the last session of OOPSLA. Here we're going to be talking about a number of papers on separation logic and verification. So the first paper will be verification preserving inlining in automatic separation logic verifiers. It'll be presented by Thibault Dardinier, joint work with Gaurav, Parthasarathy, and Peter Müller. Yeah, I'm looking forward to this because we're using this tool in some of our work. So,
thanks for the introduction. So I'm really happy to see a crowd of passionate separation logic people, passionate enough to be there on Friday 4 p.m. So let me jump right in. So our motivation here is bounded verification. You don't have to read this code. Just know that it ideally should compute, should do a fast modular exponentiation, so x to the power of this exponent modulo k, which is used in cryptography. And imagine you write this code, your end goal is actually to verify it using an automatic verifier. But here you would like to have a quick feedback on your implementation. Is your implementation at least correct? And what you can do is check a few properties that the rest of the code depends on. For example, the result should be between 0 and strictly smaller than k, the exponent. And maybe here, because you have a tool, you run your tool, and verification fails. And it tells you that this assertion doesn't hold. But you know those tools, they cannot reason well. Unbounded verification needs a loop invariant to reason about the loop. And this, in fact, is not an actual error. This will never happen. And so the question here is, we would like a way to reliably detect implementation bugs without requiring annotation. So we would like, in this situation, to get quick feedback on our implementation. And so, as hinted by the title, what we can do is bounded verification. And in our verifier, we can achieve that by unrolling the loop iterations, like so. So here we are unrolling the loop iteration twice. You can see with the colors we guard the executions with the loop condition. And then because we unroll twice, we need to stop to ignore the executions that would execute the loop more than 2 iterations, which we do with this assume statement. Now we have gotten rid of the loop, we can run our verifier again, and now we will have this. So verification fails, but on a different assertion, which gives us first a bounded guarantee that this first assertion will hold for any input x, and k for as long as the execution is at most 2 loop iterations. And then the second one is an actual error here. So this is our goal in this work. In this work, we want to report meaningful errors to the user without requiring annotations in the context of using a verifier. And to do so, we use inlining. So inlining in this work means inlining method calls and unrolling loop iterations up to a bound. And the reason why we would like to do that is because it has already been applied, and this has been really successful. So it has been applied successfully for boogie programs in the Coral tool at Microsoft Research, and it's now powering the static driver verifier. And the question we ask is, can we replicate this for automatic verifier based on separation logic, like those non-verifiers here? And for inlining to fulfill our goal, we need an essential property. And this property is verification preserving. So inlining is verification preserving if any error in the inline program reveals a true error in the original program. So in the examples we had before, the error that we had in the inline program corresponded to an actual error in the original program. By the way, if you're still wondering, it's if we don't enter the loop, we got that this assertion doesn't hold. And so the good news, the reason why Coral was successful was because this property always holds when we don't have separation logic and in the context of boogie programs. But when we add separation logic into the mix, it does not always hold. In particular, in all those 9 verifiers, we have examples of where inlining is non-verification preserving. So now let me tell you why this property does not always hold. And for that, I'm going to use an example based on VeriFast. So VeriFast is a verifier based on separation logic for Java and C programs. And in VeriFast, here this is really simplified, but there is, for example, a library to manipulate locks. So this library does not have an actual implementation, but is axiomatized by pre- and post-conditions in separation logic. So we have here a way to allocate references that does not require anything and returns us a resource own of L. We have a method with which we can create a lock. And you can see here the precondition requires own of question mark x. And that is very fast syntax to existentially quantify over an argument. And in particular, x is going to be bound at the call site so that it can be reused in the postcondition. So you can think about own of x here as, this is a simplified example of existentially quantifying over an invariant so that we can put an invariant inside our lock. And then we can acquire this lock. So we just require to know that we have a lock of LA, and then we will get access to the invariant. So now we can write a client, for example, a main method that allocates two references A and B, and that calls a method N, and N will just create a lock and then acquire it. So now the question is, does this program make sense? Is this program correct? If we run our verifier, if we run very fast in this case, verification will fail. But it might be because we don't have any annotation here. So we want to perform inlining. And to perform inlining, we're going to first take the body of main, put the two first allocations, and then we're going to replace the call to N by the body of method N. And now, let's see whether this program verifies. So to do so, if we run very fast, this program doesn't verify. And to explain to you why, I'm going to walk through the steps that the verifier takes. So the verifier starts with an empty context, so it doesn't have any resources. And then when it allocates, after the first call, it gets, it has in its context own of A, because this is the postcondition of alloc. Similarly, after the second call to alloc, we have own of A star own of B. And now comes the crucial piece. When we want to verify the call to create lock, we have to resolve this existential. And we have two ways to resolve this existential. We could choose to satisfy the precondition with own of A or own of B. Here, for reasons that I'm not going to explain, the very fast heuristic instantiate X with B. And so it's going to exchange own of B with lock of LB, and it's going to keep own of A. And this is really the issue that we have, because then verification will fail here because acquire requires lock of LA, but we have lock of LB. So here, this is really the heuristic made the wrong choice. But if now we would have written this annotation for the method for original program, verification would verify. So that is really, this example really shows why inlining can be non-preserving in automatic verifiers. This is because with annotations we can restrain the choices that are made by the heuristic, whereas in the inline context, here we have more. So to summarize this key problem here, inlining modifies the resources that are owned by method execution. So because of our annotation in the original program, we just have own of A. In the inline program, we have more. And this affects automatic proof search algorithms. So in particular, here it affects the heuristics. How do we resolve this existential? So this leads me to the contribution of this paper. In this work, we identify this problem and its causes. But it turns out that in practice, many programs are can be still inline in a verification preserving way. So to prove that, we derived a theoretical solution that we call the semantic condition. This condition is a condition that we can check on inline programs without annotations that ensures verification preserving inlining. And the keyword here is compositional. Verification preserving inlining, this property is not compositional. It corresponds to the two programs. But this semantic condition is not. It's still a bit too hard to check automatically, so we weaken it to a structural condition that is easier to automatically check. These two solutions have been formalized in the Isabelle proof assistant for a parametric verification language that essentially captures the automatic verifiers for separation logic, GRASShopper, VeriFast, and Viper. And to show that, I don't know why the arrow is there, it shouldn't be, but to show that our solution is practical, we implemented an inlining tool for Viper. And finally, we evaluated those 4 contributions based on the test suite of GRASShopper, Nagini, RSL Viper, and VeriFast. And all our implementation, our evaluation, and our formalization are available in the artifact. So in the remainder of this talk, I'm just going to talk a bit about the semantic condition, what are the key ideas behind it, and a bit of the evaluation. So if we go back to our example before, remember that we had an example where inlining is not preserving, so we have a false positive because the inline program fails, but we can find annotations such that the original program verifies. If we zoom in a bit, and if we rewrite the original program with a hard triple, we see that this is really the issue that we have. We have the same program in both cases. We create a lock and then we acquire it. But in one case, if we only have on of A, it verifies. And in the other case, having more resources makes verification fail. And this violates a condition that we call safety monotonicity. And this condition basically says that adding resources shouldn't make verification fail. So what you can see here, the index V means that this is with respect to an actual verifier. This is not a theoretical proof. This means that a verifier V can verify the statement S in an initial context P, and its output context will be Q. And so to be safety monotonic, in every larger context P star F, it should also verify. But our semantic condition uses three key conditions. That's the three key properties. That is the first one. A second one that is stronger is monotonicity. And the main difference with safety monotonicity is in this output context here. So in the first case, we just require any output context. For monotonicity, we require that adding resources cannot make the output context smaller. So if in the original case, the output context is Q, we should have something that is larger than Q. And the third and final condition is extremely related to the frame rule of separation logic, which we call framing. The difference, again, is in the output context. And it means that additional resources should be at least preserved. And so now just to make clear again, if you just think about separation logic in a theoretical way, all those three properties should trivially hold. I mean, the last one is the frame rule. That is one of the core rules of separation logic. And the other one are weaker. So the key point is that this is really for a given verifier. And so why do we have three key properties? The reason is that they apply to different parts of the program. So if we look at a simple example here, we have a main method with two method calls and three blocks without any calls or any loop. We will require the inline method bodies to be framing. And the reason is that automatic verifiers apply the frame rule, but explicitly only at call sites. The block in the middle must only satisfy monotonicity, which is weaker, because no frame rule is explicitly applied there. And finally, the last one doesn't need compositionality, so it must only satisfy monotonicity. So this is a simplified picture. There is actually more in the paper. But now I just want to convince you that this is an actual problem and that our solution is effective. So to evaluate this, we have taken files from 4 test suites, so GRASShopper, a verifier for a decidable fragment of separation logic, Nagini, a Python verifier, RSL Viper, a verifier for C++ program, weak memory C++ program. Both RSL Viper and Nagini are built on top of Viper, so they can benefit from our tool. And the last one, VeriFast, is a verifier for Java and C programs. So taken together, that gives us more than 1,500 files. And then we wanted to know whether first, these files use features that could potentially lead to non-preserving inlining. And we did that automatically with syntactic check by looking at the features that could do this. And we found that at least 2/3 of these files could lead to non-preserving inlining. So which means that we need some solution for that. But then we wanted to know whether non-preserving inlining actually occurs in practice, and we cannot do that automatically. So we sampled randomly for manual analysis 72 files from the 4 verifiers. And we asked the question, does non-preserving inlining occur? And it turns out that in 1/3 of the cases, for 22 files, it does. But for a majority, almost 70%, it does not. And so finally, we wanted to evaluate our conditions. So for those 50 files where inlining is always verification preserving, 49 files are captured by our semantic condition, and 47 files are captured by our structural condition, the one that is implemented in our tool. So that's what I wanted to say today. So to summarize, our motivation in this work is bounded verification. If you're using a tool to do unbounded verification, you would like to have some quick feedback without writing annotations, and you can do so with this, with inlining. But you need inlining to be verification preserving, otherwise you could get false positive, and it wouldn't be really useful. in particular, our main contribution is this semantic condition and a weakened version of this that can be checked automatically in a tool. And our semantic condition, as I said, is based on 3 key properties. But the key insight that I want you to remember is that those 3 properties are really based on the verifier. No theory of separation logic usually looks at this automatic verifier, which is why this problem was never really discovered before. Thank you for your attention.
Thank you. Are there some questions?
Thank you very much for your talk. It was very interesting. I wanted to ask, so if I understand correctly, you only allow inlining some method bodies if they satisfy the framing condition.
So that's not exactly what we do. Is that if you use our tool, we inline everything, and then we check whether the method bodies that we inline satisfy or not a condition. And the question is, if we find an error somewhere in the inline program, we are going to check whether this might be a false positive or not.
Right.
So it means that if you have, in some cases, in some places, some methods where framing is broken, then we cannot give you high confidence error messages here, but in other places we can.
Mm-hmm. Okay, I see. I just thought that it might be useful to have a statement in the language where you have a block and you say that this is the only part of the outside context I'm going to access, right? Because then you would essentially be able to add this sort of, after you inline, you restrict the outside context.
Thanks for.
In your framing property, why do you have this existentially quantified R in the post condition?
That's a really good question. The reason is twofold. So one reason is that R, you can think about it as, here I didn't show the formal definition, but you can think about it first as R giving us pure information, right? Not just resources. And in the inline program, you're typically, for many reasons, going to have more information. Even if you just allocate a new reference, knowing that you have other resources in your context will give you non-aliasing information that is not going to be there. That's one reason. The other reason is that we are not tied to a linear or intuitionistic separation logic, linear or affine. For example, GRASShopper has a classical separation logic, and here it's really important to say that it could be more. And finally, we found some examples in RSL Viper where you don't need the frame rule. So this is not the frame rule. The frame rule would be some equality, right? If you have some resources that maybe you clone, this is going to satisfy your framing condition. But this is not really the frame rule. Does that make sense? Yeah, we can take this offline.
All right. One more quick question.
Okay. Hi, Thibault. Are you still listening? Okay. Okay. So you said there is some arcane reason why VeriFast chooses B in the existentially quantified permission case. So would you say this is then a bad heuristic also now with this view? Should heuristics actually preserve inlining, or is there a good reason for it to do that?
Sorry, could you speak on the microphone? Yes. So I don't think it's a bad if you wanted a heuristic that preserves verification preserving inlining, your heuristic would be basically you have a demonic choice and you take one in one execution and one in the other. So that would be strictly worse. I think their heuristic, mostly I think their heuristic is based on the fact that they want to be faster, and the way VeriFast is implemented, you just use the first choice that you find. And I think it's just good to have heuristic. It's just also important to be aware of this problem. But in general, there's something in our evaluation that shows that many cases where you have existentials are still captured for reasons that are beyond the scope of this talk, but that are in the paper.
Great. Thank you so much.